Hello, this is a description of the skeleton code for the June 2023 AQA AS level computer science exams. Well, exam single, this is only for paper 1, thank God. Okay, let's scroll back up to the top and let's go through this. At the top we have all these constants. How many of these? 1, 2, 3, 4, 5, 6, 7, 8 constants. The first one, simple enough, like as this comment says, it's an empty string. This is going to assign 20 memory addresses. This is the maximum integer, but because it is 2's complement, the maximum integer is 127. The minimum integer, the lowest number you can go to, is negative 128. Now these are determining the positioning in a registers array that we will come to later. So for now, we will actually keep these constants stored separately in a text file as well, just to keep them safe so we can refer to them instead of having to scroll all the way up and down, up and down, up and down. Right. Now we have a class here, assembler instruction. This is creating the memory locations, and this is the initialization procedure. It's going to have an opcode, an operand string, an operand value. This, don't worry about it, we can come to that later if necessary. But from here on out, it's just a lot of functions, procedures, and it's a lot. So we will scroll to the bottom, and we have this: if name equals, if underscore underscore name underscore underscore equals underscore underscore main underscore underscore, right? So this is to do with inbuilt features for Python. So each Python file will have its own metadata of sorts. Like this underscore underscore name, it's similar to the class type thing. By checking if it's main, it's checking if it's the main program and it's not been imported to another program as a library. Like, let's say if I've imported this and then I just call the assembler simulator program, right? That's not how this works. So if it's the main program, then it'll start with calling this and then assign everything else, you know? That's how that's going to work. Now, since it does start with this, let's get to it. Assembler simulator. We are creating a source code array. We're creating it through empty string for lines in range HIMEM, lines temporary variable. The range of HIMEM, which is 20. So 0 to 20, but because the end value is exclusive, 0 to 19, but that's still 20 values. So 20 times we're going to be adding an element to the source code array, well, as an empty string. So we then have memory, an array, and for lines in range, HIMEM. So again, same thing as this, it'll be 20 items that we're making, and we're going to call on the assembler instruction class at the top here. So every time we're calling on this class, we're actually making a new object. So that means the memory array, each index position will be storing an assembler instruction class object. So memory position 0 will have its own object, memory position 13 will have its own object, and so forth. Now we go into this function where we are resetting the source code. Basically, for line and number and range, there's 20 iterations going through each element in the source code. For each element in the source code, we're just putting it back to an empty string. This is just keep it going, you know. So let us go back, if it will let me. There we go. Now we are going to reset the memory as well. So for line number in range HIMEM. Now because it's a class in a class object from a class, object from a class in each index position, we can't just create it to a new class because that's editing the entire thing. We have to edit the object itself. So we call on the different attributes, the opcode, operand string, operand value, and we put them back to what they were originally, empty string, and 0. So now we come back to Assembly Simulator, and we have this. It is defining finish as false, and this is going to play into the while loop. While not false, so while true. If it's true, the while loop is going to run. So first of all, this I'm fairly certain is the only procedure. Display menu. It's just going to print all the options, and then that's all it is. Nothing too hard about that. Then this is the function of getting the menu option, assigning choices an empty string, and this part here, the while the length of the choice variable is not equal to 1, then it's going to be having a validation check. It's going to keep on asking. Now here, choice 0, this is like, it's redundant, unnecessary. It's only going to be one character, so there's no point having this, which is weird, but fine. Now we're checking a bunch of if and elif statements. We are starting with if menu option equals L, loading the file. So if we are loading the file, then we have to load the file through this function. File exists equals false. Source code, again, being reset. Line number 0. And then we're inputting the file name. Now we're not taking the .txt here because in this try except block, we're going to be formatting it in a way such that it is actually going to add the .txt itself. We're opening it in read mode because we don't want to be editing the source code. So if this does work and there's no error, it can go to the next line and say file exists equals true. Then it's going to read the line. While the line of the code is not an empty string, line number is going to increment by 1. Now you have to start at 1 because source code position 0 will be containing the number of lines that there are in the code in the text file, as you can see down here. So source code line number is equal to instruction, everything up to the last value. You can have negative indexing in arrays and lists, don't forget that. So this -1 isn't some imaginary value, it's indexing backwards, so it's actually taking the last position, the last character in the line. Now, because it's a multi-line text file, it's not actually taking a character per se, it's taking the return thing. So what jumps you to the new line. That's all that's being removed, as you can see here. Now, then it's going to read the next line, and then goes back through this while loop until, of course, instruction is an empty string. And I know we can't see it, we can't see this /n, but the computer does. So even if you just spam enter and have new lines, it looks empty to you, but it isn't. So that's going to happen without any errors. And if there are no errors, it will jump to here. If line number is greater than 0, then it will display the source code. This occurs if there isn't an error when reading the first line. Let's double check that actually. I have a list of the error codes open here. So error code 2, number of lines in the file is greater than the number of available memory addresses. So this is incorrect. Ignore that, I suppose. But let's go back to this except block. If not file exists. Now, if there's an error here in opening the file name, then this does not happen. So file exists is remaining as false, as shown here. So if not false, if true, error code 1, the file doesn't exist. But if the file does exist, there's an error with reading the file. So error code 2, this is interesting. We could double check this. Let's see, shall we? So let's load it. L prog 4. There is no error code here. Why? Because there's still that \n. So this is wrong. Or if there's an empty line in the code. That empty line, that can't be happening, as I have previously explained. So this previous comment is incorrect, and we will be sticking with what has been shown in this document here. Number of lines in the file is greater than the number of memory addresses visible. Now, if this has happened, then it will take the length but subtract by 1, of course, because you've added here. So let's say you read the 20th line, right? Because source code 0 is going to store the number of lines in the code. So let's say you stored, you read line 19 here. Here you have read line 19. So 1, 1, 2, 2, 2, 3, 3, 4, 4, 4, 5, 5. So the line number will reach the line number, and then it reads that line number, right? So it has to have it one ahead. So that's how it works, okay? And then it's going to assign it, but because it's reading a line greater, it can't be doing this, because otherwise there's an error, because you're trying to access index position out of range of the array. That's a runtime error. So that's going to raise a flag error, and then you go into this exec block. So that's why you're doing this. And it's a string because the source code array is storing string formats. So that's how that is working. Let's go to display source code. You're printing a new line just for formatting to make it look nice. And then you're taking the number of lines in the code file, then for line number in range 0 to the number of lines plus 1. We have the plus 1 because, again, it's exclusive, so you have to iterate through this number of lines. This is formatting right here. So we have dot format line number will go into here, and source code line number, that's just taking the line of the text file into here. Now this colon, that's going to be placed, let's show, for example, instead of having that, I have this. Right? This is the same thing as this entire section here, ignoring this, of course. The variable name is going to come before the colon, and then these are the formatting rules. Okay? So this is an arrow pointing to the right. That means this is going to be right justified, like the text is going to be pushed onto the right side. The 2 will say that there's a maximum of 2 characters allowed for this formatting, and the D is saying that the data types can only be of binary or integers. Now here it's the same principle, but it's pointing to the left, so it's going to be left-aligned. It's 40, so it's a maximum of 40 characters. S meaning string, as you can see here. Then it just prints a new line, and that's done. So turns out this is also a procedure. We have 2 procedures, display menu and display source code. And once we finish this load file, we return the source code and we come back to assembler simulator. That took too long. Anyway, memory, resetting the memory, same thing, because say you've loaded prog1.txt and then you want to load prog2.txt, right? You have to loaded prog1.txt, and then you run that, and then you're loading another file, right? You have to reset the memory, otherwise you have the memory information for prog1 that you don't need that, you don't want that. So now we jump to the next menu option, displaying the source code. If there is nothing loaded, by checking the first position, if there's If the file hasn't been loaded, then it's going to print out error code 7. Now, this is only if the file has been loaded. If a file has been loaded but it has 0 lines of code, you create a text file, it has nothing, ignore all these previous lines, it only has this, just a blank line, then that is irrelevant, right? That's not going to cause an empty string. That's just going to say there are 0 lines of code. So this does not happen. And it will display source code. It will just print that there is obviously no lines of code. That's what it's going to show. It's starting at 0, so it's going to show 0, 0. That's all it's going to print. That was relatively simple. Let's move on to menu option equals E, edit. Now, again, same principle is here. If nothing has been loaded, you can't edit it. Otherwise, you will edit the source code and then reset the memory. Like, what if I've loaded prog1, I've assembled, I've run it, and then I realize, oh no, there's a typo somewhere. So then I have to edit it, and if I'm editing it, I clearly want to assemble and run it again, so I have to reset the memory. This is somewhat complicated, but it's honestly fine. So we're taking the line number, enter the line number of code to edit. If I want to edit line 11, I enter that in, and then it takes input, converts it to integer format. It prints out that line so I can see which line I've selected. Then it will take my choice. While choice isn't C, which is cancel in the code, choice is still an empty string. And while choice is not E and choice is not C, it will give you the option to E, edit the line, or C, cancel the edit, and then ask for your choice. If it's E, it will allow you to enter the new line and assign it to the correct index position. It does require the user to type the code correctly with proper formatting for the opcode, operand, etc. If, for example, I load prog1 and I want to edit line 5, okay, let's show, oh no, I've missed a space. In fact, no, let's not do this. Let's not do this. I will actually do it properly and then I'll show you something. Just hang on. Let's cancel edit, go back. We will choose line 9, jump while. JMP space WHILE. As you can see, it's not formatted properly. It's not added those spaces in. So that is not something done by this subroutine. If you want that done, you'll have to add it in yourself. And don't worry, this editing, it's not actually saving it to the text file. If you want that done, you'll have to do it yourself. These AQA programmers, they're so generous, aren't they? It's editing, it's displaying, and then that didn't happen. You didn't see that. Editing, it's displaying, and then we reset the memory. Then here's assemble. This is a semi-long one, but it's not as bad as this. We'll get to that. So again, same principle as for E and D. If there's nothing loaded, you can't assemble. If there is something loaded, we jump into here. We're taking source code memory, but we're only editing the memory because we're assembling. We're not editing the lines of code. So we jump into assemble. First, we reset the memory just for good measure because these AQA programmers, they're paranoid. Allow it. It's fine. We take the number of lines in the code. And here, this is symbol table with these curly braces. It's not an array, it's not a list, it's a dictionary. A dictionary will have keys and values. We'll see that in a moment. Now that it's defined this, it's going to save memory and symbol table as whatever is returned from this function pass1. So it will take the number of lines as the first index position in source code array. then it iterates through each line. So it will take the entire instruction and then again saving symbol table memory from this extract label function. If the length of the instruction, the line of code, you can go away, if the line of code is greater than 0 characters, if it's not empty like these, then it will take the first 5 characters. By taking this, the 5th character is the last one taken. So if we start here, this is the 1st, 2nd, 3rd, 4th, 5th. We then strip, so we are taking away any spaces. So let's say, for example, we've actually taken num3, 1, 2, 3, 4, 5. But wait, there's a space, so we remove that. And then we check, is it an empty string? Because what if we've taken this? All of these are spaces, right? So the first 5, they're going to be all spaces. If we stripped it and it's empty, we don't need to bother with a label. There is no label, because the label is what has the colons. There's nothing there. But if there is a label, then we check if instruction position 5 has the colon, because if it doesn't, that means the colon was included into the symbol, the label, so obviously it wasn't formatted correctly. You have to add a space to make sure that the colon is the 6th character in each line of code, because there will be errors otherwise. And if this error has occurred, error code 4 will arise, and then it will tell you that in the first object in the memory array for the opcode, there is an ERR. There was an error during assembly. Otherwise, it will update the symbol table. If there is no error, it is executed perfectly. Well done, mashallah. Congratulations, it's going to update the symbol table. If this label, now what's this label? It is actually what has been extracted from the instruction line. So if the label is already in the symbol table, then there's an error. So if you have, oh no, multiple while loops, oh no, the computer cannot understand which one to jump to. So it will panic and it will tell you, no, don't give me that, go away, here's an error code 3. But if there is nothing, if it is new to the symbol table, it's just moved into town, give it a housewarming party, let it into the symbol table, and then take the line number. So the instruction label is going to be the key, and then the value is going to be the line number that it is on. Then it returns symbol table. And that is the end of extracting the label. So we go back even more. And we extract the opcode and save that to memory. If the length of the instruction is greater than 9, then we are going to have this list of opcode values defined. We are going to take the operation as the 3 characters. So it is going to be these. So if these are the first 5, this is the 6th, this is the 7th. So this 8th, 9th, and 10th characters. If the length of the instruction is greater than 10, so that means if it's not just an empty opcode, then we are going to check if there is an addressing mode. Like for the hashtag, we take that next character, check if it's a space or a hashtag. If it is a hashtag, then we add the hashtag to the operation so that we can check against it. If the operation is in opcode values, then it will assign the opcode to the corresponding object in the memory array and add that to the opcode attribute. But if it isn't, then it is going to check if operation is on an empty string. It's doing this to validate just in case you have something like this. A label, no opcode, and an operand. If there's something like that, then you don't need to worry about it. But if there is an opcode and it is not recognized by the computer's instruction set, the opcode values Then it will print error code 5 and assign an assembly error to the memory objects, to the memory array. And once that is all done, we go back. That was not seen. Hello? There we go. We are going to extract the operand. Now, if the length of the instruction is greater than or equal to 13, then we are going to start taking the 13th value and work our way onwards from there, all the way to the end of the line of code. It ignores the line number and the opcode. We take this position as -1. This is going to be checking for a comment, which is signified by an asterisk. Now, we start at -1 just to assume that there is no comment, because that is for checking this if statement. So we iterate through each if operand position is an asterisk. This position is going to be assigned to whichever value has been found for the position of the asterisk. Then we check if it's greater than or equal to 0, and we change the operand to everything except for the comment, so that the code does not break during execution. Now that we have that, we are going to take the operand and remove any and all spaces with the strip function, and then we are going to assign the operand string to the operand. We then return the memory, and that is pass1 complete. We return memory and symbol table, and now we jump to this. If there is an error, well, if there isn't an error, then it will allow you to have jump as the opcode for the first index in the memory array, because that is how you're going to start your program during execution. You need to figure out where to start from, so this is how it will tell the computer to do it. Then this is the only opcode, right? So it needs to know where to jump to. You can't just tell it to jump. It might jump on its head and die. Who knows? First, you check if start is in the symbol table. This is an example of AQA programmers thinking good programming practice, so we'll add something like this for the students to cry about. We check, is there a start in the symbol table? If not, then we will be having the jump start at the first line of the code, so that it's going to be 1. But if there is, then we take the value for the key of start in the symbol table, which is the line number, as I've said before, and we add that into the operand value. So once that is done, we head on to pass 2, which I do not like, but I don't like any of this code, so I can't really complain. We're iterating through the number of lines, and the operand is going to be assigned as the operand string. So here in the memory, we have memory, symbol table, and the number of lines. That's what we're taking into pass 2. We are creating an operand as this operand string. The operand string is going to hold the operand as a string, obviously, and then check if it can be converted. If there is no operand, then it just jumps straight back to returning. But if there is an operand, it checks if the operand is in the symbol table. Like, for example, STA num3. This is an operand, and it's in the symbol table. So that means it is defining a number. It is a variable. So if it's in the symbol table, then you have to assign this to here. We are loading the line number of where this is stored into operand value. And then we assign this operand value into the corresponding line number and its memory address. Let me show you again really quick. In pass 1, we have pass 1 here. We are extracting the operand, but that's not how it works, right? We extract the label, we're checking, and we're updating the symbol table. if this label is symbol table, we're adding the line number, not an operand. Just so you know. Definitely wasn't so I could double check. Totally not. Anyway, but if this isn't in the symbol table, then we're assuming it is just something that can be converted into an integer. So we try that, and if it works, then we assign that to the corresponding line number and memory address. But if there's an error, then there's an error with operand during assembly. So we assign the ERR to show that there has been assembly to prevent the running of the code, or to show that there is an error with the running. That is assemble complete. Bane of my existence, running the program. Well, it's going to check if the operand value is 0, because this is going to hold the line number you're jumping to, as shown here in assemble with pass2. For each line, wait, what? I did a dum-dum here. Wait. Wait, where's my dum-dum going? Ah, yeah, here. Oh my god, I'm tired. Anyway, I need coffee. Anyway, if there is nothing you're jumping to, then, error code 10 is occurring, because, as you're seeing here, it's going to check, right? It's either going to take the line number or 1. If it's telling you at 0, then that's not how that works. You can't start from where it's telling you the number of lines of code that's going to break it. So then it checks if there's an error in the opcode for the first memory address, then there is a runtime error, or error in assembly. Sorry, not a runtime error, ignore that comment. Now we have execute, this wonderfully long function all on its own. That's not even a function, actually. It is a procedure because it doesn't return anything. Congratulations, we have 3 procedures. So, wait a second. Registers array. When did we talk about that? When did we talk about that? Oh my god, right here. Program counter, accumulator, status register, top of the stack, and error. Just error. This is actually telling you the index positions. So the program counter is this, the accumulator is this. Can you see my mouse? Program counter, accumulator, status, top of stack, error. Now it's going to set the flags by taking whatever is in the registers ACC as its own separate variable, local variable, and then registers. To go into that, we're taking registers ACC as a value. If value equals 0, then we are converting 4, right? But if we take a look at this 100, let us do a little funky showing right here. This Z and V, now, if you haven't run the program by yourself and looked at it, I don't know what you're doing with your life, but I'm sure you've seen this and you've wondered. In each frame, you've seen this and you have wondered, what is this? Most of you probably know what this is by now. I'm hoping all of you do. But if you don't, here you go. The Z means whether it is a 0, the N means whether it is negative, the V means whether there is an overflow error. If value equals 0, then it's showing a 1 for Z, a 0 for N, a 0 for V. This can also be found in the preliminary material, which again, I'm hoping you have read, because otherwise I don't know what you're doing with your life. Else, if the value is less than 0, it is loading 1 for negative only. Here it's checking if there's an overflow error, so it's loading a V with a 1. But if there's nothing wrong, then it loads 0, 0, 0. it is a positive value and there is no overflow error. But see, funny thing here, it doesn't check for a negative overflow error. But no, the programmers at AQA, don't trust me. They're too good. They want us to suffer. They're gonna make us do it. Very fun indeed, you know. Anyway, we go back to here. We are telling the program counter the next line is 0, line 0. Congratulations. We have the top of the stack as 20. We'll come to the stack in a little bit. Don't worry about it. Frame number starting at 0. This is the introductory frame. Like for any book, you have an introduction, right? This is that. Display frame delimiter. If frame number equals -1, it's gonna print all these asterisks. Now again, please, I'm assuming you've run the program, you've seen the frames. The top of each frame will have this, the bottom of each frame has this. This is just the footer. So for those of you that were not understanding or potentially argued about this, it's the footer. Don't make a mountain out of a molehill. You know who you are. Alright. So we've displayed the frame delimiter, frame 0, you know, so it's not -1, so it's printing frame 0 as the header, and we're displaying the current state of the program and what's going on. So we print this, we're displaying the source code, we print asterisk again, and then we're printing the status of each register, the register that is important, of course. So here the program counter is showing you which next line is going to be executed. Accumulator, what is in the accumulator, top of the stack, and it's just like sort of like the stack pointer, you know. So here you go, you can read. Then it's going to print the status register, and it's going to be printing this to format with this, and then it's going to print, well, it's taking the status, right? The status has been loaded as whatever check values have been checked from that set flags function, right? So it takes that decimal value loaded into status, converting it to binary. So this is interesting, right? Binary string starts off as an empty string, while decimal number is greater than 0. You can have 4, you can have 2, you can have 1, you can have 0, while it's greater than 0. If it is 0, then you don't need to do any of this. While length of binary string is less than 3, then you're just adding 0 plus 0 plus 0 plus 0 plus 0. Congratulations, there's no errors, and then you just return it. Let's say it's 4. Okay, there's a 0 thing, a 0 flag. The accumulator is equal to 0. So 4 is greater than 0. 4 modulo 2, so it's finding the remainder. So the remainder is equal to 0. But this is going to be taking the string of the integer, and it will have this assigned to string 0 plus an empty string. And then we integer divide by 2. So 4 integer divide by 2 is 2. And then we go back. 2 is greater than 0. 2 modulo 2 is 0. Then we have 0 plus 0. And then we divide by 2 again. That's 1. We are going to then modulo 2. 1 cannot be divided by 2, so the remainder is 1. So bit is now equal to 1. That's new. Wow. 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 Owen Wilson. Sorry. Binary string is now equal to 1 plus 0, 0. So the resulting binary string is 1, 0, 0. Hey, wait a second. That's the ZNV status for when the accumulator is 0. Well, yeah, that's what I've just been talking about. So, yeah. And, oh, look, here's the footer. Printing the footer of the frame. Wow. I'm only this in like 1 year, I'm sorry. And then registers PC So it's loaded up all of this, right? Then when it's loaded up all of this, it's this program counter, it's actually going to be equal to 1. Yeah, no, I'm kidding. It's not. Right now it's at 0 because it hasn't been changed yet. So it's going to take the opcode value for this, and that is actually going to be your opcode. While your opcode is not halt. Now the first opcode, you have frame plus equals 1, so it's going to start at frame 1. Now your first opcode is going to be jump. So first of all, it will display the frame delimiter by showing frame 1. Okay, it's going to do that. And then it's going to take the operand value. So because it's jump, it's going to take the line number for start, or just the line number of where you're supposed to go to. It'll print the current instruction register. It'll tell you the opcode. It'll tell you the operand. Okay. Now, this if you have start in the symbol table and you have jump start, then because the start is on say line 5 for prog1, you're going to jump to line 5, right? So once you have this operand, actually now it starts having the program counter as the next line of code, because that's what it is. Now it checks if it's load, it's not. Checks if it's store, it's not. Checks if it's load with immediate addressing, enter hashtag, it's not. Checks if it's adding, it's not. Checks if it's jumping. Ooh, it is. Let's go to there. Let's execute jump. We're just telling you which, like, it's taken the operand as the address here, operand equaling address, and it's telling you you're not gonna go where I want you to go. You're gonna go here. You're gonna jump here. So jump to line 5 or wherever it wants you to jump to. And then it's executed this. Doesn't need to check through all of these because a condition has been fulfilled. So then it comes back to the while loop. It checks is the opcode not halt? No, it is not. Thank God. Then we increment the frame number. We display the frame delimiter. We take. Now we're actually taking the next line, like this next line. We're actually taking it, right? So line 5, we take the operand value, and then we load it into operand. We show the current instruction register, which for prog1 will be LDA num1, right? Loading num1, LDA num1, but it's going to be showing slightly different. Likely it will just say LDA2. In fact, we can test that right now. Let's test that right now. L prog1. Let us assemble. Let us run. We are on frame 1 here, as I said, jump 5, jump to line 5. Now LDA1 is telling you the line number to refer back to because num1 is a symbol table belonginger. It's a label, it belongs to symbol table, so it's taken that line number and it's taken that operand value and then it's loaded it in. Okay, that's why. And then it increments by 1, so now it's actually ahead by 1 and it's just checking, right? So let's start going through all these executes. If we're, oh, interesting, let's actually take a look. No, we'll do a principle. We're executing LDA. We're taking memory registers and address is the operand here. Okay, operand is pretty much going to be the address in each function. So registers, the accumulator is going to be taken as the operand value. You're loading it into the accumulator, and then you're checking if there's an overflow or a 0 or a negative or anything, and you return registers. Simple. STA is the opposite of LDA. You're just loading whatever is from the accumulator into the memory. You don't need to check if there's an overflow or anything here because it's going to be checking this throughout the program. So once you're loading it back into the memory, It knows that yeah, this value is valid. We can kick it out, send it on its way. It'll live, it'll survive. It's okay. Now this is just immediate addressing. It's going to directly take the operand rather than the memory address in a convoluted format, and then it will set the flags, check, and come back to registers. Then we have execute add. So it's just a simple AND operation. Accumulator plus whatever you're adding, set flags. Now, if there is an overflow error, then it will report that runtime error. So once you've once you've executed this, right, then well, say you've executed this, there's a runtime error. Okay, it'll say overflow. You've gone here, then you know, you're putting a runtime error. So like for prog1, and the end result will get you a runtime error, and it doesn't actually print the frame in its entirety. So let's go into this and let's show you. So print runtime error equals error message, and then it's telling you there is an error in the registers, of course. Okay, what I said previously about not checking the rest of these, yeah, that was dumb. It does check the rest of these. Oh no, it doesn't check the rest of these. This is a new if-else statement. So it skips all these alifs and then jumps to a new segment of if-else. I know it doesn't look like it, but it might not look like it, but they are different. They're different segments. So it's checking if there is an error. Okay. If there is no error, then it will take the opcode and it will display the current state. It'll show all the source code and the status for everything else. As you can see here. But if there is an error, then it'll change it to halt. It skips showing all this, and then it breaks this while loop, terminates the execution. So let's assume there is no error. Okay, please. Execute jump, we've covered this. We have execute JSR. This is fancy schmancy. This has a stack in it. We'll do that at the end. Execute compare with immediate addressing. Note how there's no direct addressing here. Fascinating. Wow. Wowzers. Anyway, we're checking the value minus the accumulated value is equal to the accumulated minus the operand, and then set flags. So if accumulator equals operand, it will equal 0. So the Z will actually represent that they are equal. But if that does not happen, if it's less, then it's going to show the less than sign through the N flag. If it's greater, then obviously both are going to be equal to 0. And if it's not equal to, then it will either, it cannot have the Z flag equaling 1. So there's a little hint there. Let's go to BEQ. We're checking flag Z. If it's 1, then we jump to that, or we branch to that line, as the assembly language would say. Then we come back, right? We're obviously converting to binary these values, and we're assigning to status register. We then check the first character of it, and then we check if it's 1, and then as I've said. So let's check execute sub. We're just accumulator minus the operand value, and then we set the flags, check if there's an overflow. How could an overflow occur here? If you're subtracting a negative value, then it's like 2 minus 125. That's 2 plus 125, right? Or better yet, 3 minus 126. That's the same as 3 plus 126, which is 129, and it's overflow, positive though. But if it's 0 minus 1 minus 259 billion, okay, like this for exaggerational purposes, then obviously it's going to be less than 128, negatively, So yes, overflow, negative, but what can I say? Anyway, we've executed stuff. Execute SKP. This is my favorite function for the execute function. My favorite function inside that. Here's why. It doesn't do anything. That's it. Now return, this is to do with the stack. So we have to tackle this execute JSR. We have stack pointer, which if you remember, it starts off as 20. Okay? We have the top of the stack storing this. It's going to start at 20. And then 20 minus 1 is 19. So now the stack pointer is at 19. And this is the last memory address because you have indexing starting at 0. So this is going to be the last memory address in the memory array. So we're doing this because we assume that the bottom memory addresses are going to be empty, because the wonderful AQA programmers have decided to assume, God forbid someone would use all the lines available for them in the program and they would leave empty lines. God forbid that happening. Nope, nope, nope. Could never think of it happening. No. So they start like this. They don't bother adding extra. I mean, honestly, I can actually really blame them. That diss was just unfair, to be honest, but whatever. I don't like them anyway. Anyway, we're adding the operand value as the program counter, which is storing the line number you're supposed to jump to after the line currently is being executed, has finished its execution. So okay, fine, that was a dumb explanation. You're on line 5, you're executing line 5. When you are executing line 5, the program counter has line 6 stored. But if line 5 is telling you to jump to a subroutine on line 79 trillion, then obviously you have to come back to line 6 at some point, right? So registers PC is equal to line 6, 6. So it stored this, oh no, what happened there? There we go. So we have it back in the operand value. Okay, it's putting the memory location where you have to go back to after finishing the subroutine. And ignore this. If you want to read it, sure, I'll explain it later though. So then we're changing the address. The address, again, it's the operand. Operand is telling you which line you're supposed to jump to, because say prog3, you have JSR sub1. The sub1, that's a label. So in the symbol table, it is storing that line number. So that operand is the line number anyway. So it's overriding the program counter with a new line number. Then it'll tell you top of the stack is now the stack pointer. Like, look, there is something in here. It's top of the stack. And if you're to go through the stack again, then you go to the next one. Look, it's the top of the stack. Like, just imagine you have a desk. The desk itself is 20 as the stack pointer. You've put a stack of papers on. Stack of papers. Okay, that's not. You've put earphones case on the desk that is in position number 19, the first thing in. So this is the top of the stack. Look at me. Look at this. Wow, top of the stack. That's what the stack pointer is doing. I'm being really rude about it. Whatever. It's inanimate. It's not gonna come out and kill me. So once we have that all done, we display the stack. So this is just formatting up here, stack contents, making it all pretty. Then we're going through top of the stack to high mem. Now 20, remember this is excluded. So it really is just checking up to 19. 19 is going to be the last value. Top of the stack currently is, that's right, it's 19. Please tell me you said it's 19. I'd be disappointed if you didn't. up to 19. So it's just checking 19, right? You've seen this formatting rules again, and obviously it's here, so I can't test here, whatever. So it's formatting. It's taking that position operand value. It's showing the different things that are in the stack, the different line numbers in the stack that you have to jump back to, right? And because it is positive iteration, whatever is the top of the stack, that'll be on top. So let's say you have three values. You have 14, you have 6, you have 9 in the stack. 14 at the top, 6, and then 9, right? It's actually going to show that 14 is at the top of the stack, and then 6, and then 9, and it'll actually remove 14, 6, and 9, blah, blah, blah. So yes, that is nice. I will give the AQA programmers that, and that alone. So execute JSR is done. And now we come to execute RTN. Execute of returning from the subroutine. When you finish the subroutine, returns it to the rest of the program. So it takes the top of the stack position, puts it in stack pointer, and then it increments because you're removing a stack item. So it's going to take that the operand value stored for that stack in the index position of the memory array indicated by stack pointer. So hopefully an empty memory address, but I mean that's what it should be without, if there are no errors. This should be an empty memory address. Should be, but it isn't for one program. You can guess which one. So it's taken the operand value, and then it's erased. Well, not actually erased. It's not even. It's just ignored it. Like if I have earphones case on top of my desk, think back to that last analogy I was giving, and then I put my keys, and then I put a piece of paper, right? If the piece of paper, that's like a little note to myself saying, hey, you gotta jump back to here, right? Okay, I'm supposed to jump back to here, done. And it doesn't actually remove the piece of paper from the stack. It just ignores it. It's like it hovers it above. It's still in the stack, but you're just ignoring it completely and you're reaching under it for the keys. Oh no, you've dealt with the keys. You're reaching under the keys for the earphones. Oh no, you've dealt with that too. Wait, no, nothing left, because that's just the desk. You can't dig straight through a desk to find anything under it. You have to go actually under. You get the gist. I hope. You're all smart, so you should. Once you have that done, you've executed RTN, and that is all there actually is. So once you've executed RTN, that's all of these. The only thing left is halt. If it is halt, then the while loop, while opcode not halt, right? But if opcode is halt, then that's going to equate to false. That expression will equate to false, and it doesn't run. The while loop doesn't run if it's false. So execution terminated. Here we are loading num1, so 2. We are comparing it to 12. It should initially be saying it's less than, cannot be equal to. So it's not equal to, so we add 5. That goes to 7. We jump back to the while loop. Check. Is it equal to 12? Is it? Is it? And so if you're writing this in actual code, then the code would be while accumulator, right, is not equal to 12. That's what it's going to be. That's how it is. Okay. we've added 5, so now it's at 7. 7 is still less than 12. So we add another 5, it's 12. So they're equal, we jump to when. We store it into num3, so num3 should have 12 in here instead of -1. And then we've added 125 because we like breaking things. We've caused an overflow, and then we're halting the program. Okay? So let's load prog2. By the way, this prog4, prog5, prog6, that's not part of what AQA has given us. This is my own testing files. So this, again, this is telling you the number of lines in the code. Now, see here, there's no start, so we assume it starts at line 1, which it does. LDA hashtag 3. Hashtag means it's immediate addressing, so it's loading 3 straight into the accumulator. 3 subtract 5, so that's going to give -2. And then my favorite function of all time, skip. And then we store it in final, which is here. So final should have -2 in the end, and then we halt the program. Let us load prog3. Hello. Okay, that was weird. Let's fix that. Okay, nice. So we have 4 subroutines, sub1, sub2, sub3, sub4. We have start. Because start is here, we assume it starts from here, which it does. So loading num1, loading 7 into the accumulator. Then we jump to subroutine 1. Now, because the 14 is part of the program counter, it's first thing in the stack. We jump to subroutine 1. We add num1. Again, we add 7. So now it's at 14. Then we jump to subroutine 2. We're adding 7 again, so now it's 21. We jump to subroutine 3. We're adding 7 again, so we were at 7 here, we were at 14 here, 21, now we're at 28. Jump to subroutine 4, we add another 7, we're at 35. And then here, RTN, getting us to go back to execute line 9, which is RTN, which is telling us to go back to execute line 6, which is RTN, which is telling us to go back to line 3, telling us to go back to execute line 3, which is RTN, which is telling us to go back to execute line 14, which is storing into num2. It is going to store the result into num2. Currently it's 0, but it will store this result into num2 and then end the program. Now, prog3 is what I want to show you. Now, I've just told you the expected value is 35. So why is it 37? Memory contents, by the way. So it's showing the memory location. So the index position is showing you the code. It's formatted it all nicely as well for you. It's showing you the label, the opcode, the operand, the comment. Interesting, it has predefined that. Okay, whatever. Now it's got the memory contents, opcode, and then your operands, right? And all this. Now, let us go to frame 0. We have stored 7 in the operand, 0 in the operand, right? 7 0 7 0 7 0. Oh look, we're adding stuff into stack. So interestingly enough, it doesn't show that it's part of the stack because it's shown here. It doesn't need to be shown with the rest of this. Stack does not need to be shown here since it is shown here. I just repeated myself. Anyway, it's still at 7 0 7 0, but here, see, the thing is, you've jumped to subroutine 1, so you got this. Jump to subroutine 2, so you have this. And then you jump to subroutine 3, you have this. Wait a second, what's different here? 7076, Oh yeah, because this is stored in memory address number 19, number 18, 6 is in 17. That's why that's happening. Interesting, but no, that doesn't matter because num2 is being overwritten in the end, right? Oh no, we have another stack being added. So 9 has overwritten this 7 in memory address 16. Does it assume that the program assumed it was empty? It wasn't. That's an issue. It's overwritten the 7, and the subroutine hasn't been completed yet. So it's going to try and add this 7, but instead it's adding 9 to 28. So instead of it executing to be 35, the program ends with it equaling 37. And that's why there is an error in prog3. Prog1, the error is overflow. Prog2, there is no error. Prog3, stack assigning errors. And that is that. So, any questions? Please ask someone more qualified than me. Please let that be the teacher. I'm really hoping so. I mean, I'm sure he is. I don't know what I'm saying. Sorry, I'm really tired. I'm sorry if that was rude or offensive. Bye bye.